Nice to see you all. Welcome to the beginning of week 5. Most of you should be neck deep into your project now, and many of you, I'm sure, will be tired from the course so far. But that's okay. We're going to try and make this week a little bit of fun. I hope you're all doing well. I think that's one of the main things. I haven't gotten a sense to chat to many of you as much as I'd like, but I'm sure you are a little bit tired. I think the best thing is that it was so good seeing so many students kind of stuck into iteration 2 last week. That was kind of shocking, to be honest, in terms of just seeing like so many of you were getting like that deep into iteration 2 last kind of Wednesday, like Thursday, Friday, Saturday, which was just awesome. So that's pretty cool to see and to understand. So keep up the good work. Yeah, I'm tired too, don't worry. I couldn't, it's weird, doesn't happen to me, but last night I couldn't sleep because I was just thinking about the lecture this morning. I was like, what do I want to talk about in it? So, first lecture this term where I've been kind of just like thinking about it so much. The only other update I have is that, again, so in terms of my internet, the NBN is meant to be installed tomorrow. The current internet I have was meant to cut off yesterday, but it's still working. So just on the 1% chance that it randomly decides to disconnect today. Give me a few minutes to get my hotspot on. But let's get into it. Today's a pretty long lecture, and I don't know how long it is because normally it's kind of shorter, and I combined a few different lectures together because I really wanted to make a big thing about this topic. I've changed the name a few times on this lecture as well, as I've kind of changed what I think I want it to be about. So apologies if you've seen that kind of update on WebCMS3. I updated on the lecture slides, but where I didn't leave this was that this lecture ended up being called Writing Good Software. Like, what are we going to talk about today, right? We're going to be talking about writing good software. That's where we came back to. It's an interesting lecture. It should give you a taste of a much broader topic, right? Like, there are topics we teach you like linting, where we teach you pretty much everything there is to know about linting. There's topics like coverage, where like you're probably not going to learn, most of you are not going to learn much more about coverage in your whole life. Some of you will. We teach you topics about virtual environment, where again, most of you are not going to go that much deeper into it. But an interesting topic is software design, writing good software. Specifically in terms of, good design. There's lots of ways you could write good software. This is the kind of lecture where we can talk about this for a bit, but this will only be the beginning from pretty much all of you on a much broader journey on understanding what makes good software. And you're probably discovering this already in your projects. You're probably going into your projects and some of you are saying, oh, don't do it like that, do it like this, or this isn't very clean, or this isn't very good, or that's really hard to understand, or that's going to give us problems later. Like anytime you have these kinds of conversations that are really focused on kind of the touchy-feely, broader elements of software, you're trying to write better software, because just because you pass tests and your code runs does not mean you've written like what a normal person would call good software. So today's lecture is about writing good software, because writing good software makes your team members happy and it makes your code less likely to break. They're the big things about good software. It does make your team members happy and it does make your code less likely to break. These are both good things that you should all care about. What are we actually going to be talking about, though, in light of this today? Well, we're going to be talking about what makes good software, we're going to be talking about elements of good design, and we're going to be talking about elements of clean code. So kind of a big, broad topic. Should be a little bit of fun. How many people do we have here? 93. Hi, everyone. Good morning. And good morning to anyone in Asia as well. Good evening to anyone in the US. I don't know how many people we have from the US here. If you're in Europe, go to sleep. Anyway, so writing good software. What in the world is writing good software? This is a lecture about writing good software. So like we have to understand what that even means, because you probably have all these different ideas of it. Generally speaking, we can consider software well written or good software if these are just 3 things. They could be summarized, they could be branched out more, but the first one is the idea of if it's tested, which is, if its correctness is verifiable in an automated way. Now, thankfully, we already did a lecture on this, so we didn't need to talk about it. But you could argue that the verification, validation lecture and coverage was also a lecture on writing good software. You know, we were trying to write good software because good software is correct. It works, right? We also want to write software that is well designed. Okay, what does that mean? We'll get to that. That means that, you know, well, at a high level, that means that the software should be planned, it should be modular, and it should be resistant to breaking changes. It just means it's kind of robust and thought out. You know, it's like it's not written by a 5-year-old who's been programming for 2 minutes, right? And you should probably notice this as well as you've gone on your own programming journey. If you look back at code that you wrote in like 1511 or even Lab 1 this term, and you think, wow, this was horribly written, you can say that about code that works, right? Like, just because it works, it doesn't mean it's good. And then the third part is like, you know, writing good software in terms of the development, which is the fancy way for saying the coding, which is like, is it clean and easy to work with? Because there are some elements of software design that are very kind of conceptual and how different moving parts come together, and you wouldn't even need to write code to say that you've done a good job writing software, where there are other things that actually are part of the writing of the programming, the code play. So because we've already done stuff on testing, we're going to be focusing a lot on design and development today, because that's kind of where our blind spots are on this topic. In terms of well-designed software, and again, I touched on this just a little bit earlier, something happens, whether you think about it or not, between writing tests and finishing code. And that's design. This thing says development. It's not very interesting. Yeah, that's design. So we have these elements of design all the time. This blue box, what in the world is it? The design of software happens when you know what the problem is you're trying to solve, right? So maybe you've read the spec and you've written some tests, right? So you understand the broad problem, you understand the specific problem, like what auth register does, but you haven't quite written the code, and you're trying to think about the smart way to do it, or the way that's going to hurt you the least in the future, or the way that's going to interact with other components the best, or the way that's going to require you to do the least work. That is a very broad definition of what we're referring to with design. So it's after you understand the problem you're solving, and you've kind of tested it in theory, but you want to think about the best way to solve it before you code. So before you finish the code. This used to say before you write the code, but then again, I changed. This is one of the things I did like 3 a.m. because I just couldn't stop thinking about it. Is like, you know, it's not about, design is not everything before you write the code. There's a big part of design that happens before you write the code, but there's another part of design that happens before you finish the code, because as we're about to see, in reality, actually, sorry, that's 3 slides away. Design is very broadly understood, and we'll chat about that in a sec. So we know design's important after testing, before we finish our code, but what is good design? You know, we keep dancing around that. So the purpose of good design is to make things reusable and modular, to make things maintainable, to make things robust to changes. There's more than this, right? And different people would have different kinds of stuff. But at the simplest way, we could say that well-designed code is simple, clear, and resists the tendency to break as the software changes or grows. And this is probably the most important part, I would say, of software design. And in fact, when I think about any conversation I've ever had about software design, it's nearly always coming back to this idea, which is that we want software that resists the tendency to break as the software grows and changes. Because a lot of software out there in the real world, in whatever facet, doesn't just kind of get written for an assignment by you from scratch and then forgotten about. It gets used for a long time. You know, the work I've been doing for the company I work with, it's like I've been doing that for 3 years now, you know, and that's crazy for me because the same job will not, and what happens is like I'm getting to the point now where I'm digging up code that I wrote 2.5 years ago that we need to use again, and you look at it and you just think, that's really like horrible, you know, you're like, that's horrible code. That code does not seem like it was designed to resist the tendency to break as the software changes or grows, because in most large code bases, your software is changing all the time. You change the needs of it, things that it uses has its needs changed, the software grows, the software scales back, things are modified all the time, you know. If you look at like an active dynamic code base, you could say that if you take a snapshot of the code of January 1, and then you take a snapshot of it, you know, in December 31 at the end of that year, more than half of the code in a code base that's quite active will either have not existed, been changed, been deleted, you know. So software is super dynamic. It's changing and growing all the time. So we want stuff that resists the tendency to break. You know, the less likely it is to break when we change stuff, the more well written, the more well designed, we would say that is. This is more critical than ever. Yeah, I wrote the word web development here. That part's not really super relevant because it's just development in general. That's just my habit from my background. But basically, software design is more critical than ever, and a big part of that is just because of the rapidly iterative nature of most modern development projects, right? So like most things you write these days are written pretty quickly. If you were to go and write a project maybe 20 years ago, you probably wouldn't be doing this like test-driven development with GitLab pipelines or whatever. You'd probably be sitting down in a room by yourself or with someone else for like a week and just finishing it and then testing it for a while. So nowadays things are just like iterated more and more and more aggressively. Yeah, so that's what good design is. And if your code is doing stuff that does not make it resistant to the tendency to break as it changes or grows, sometimes we refer to that as a design smell, right? Smell is in like a bad smell. So it's kind of like, oh, you see something you don't like and you're like, oh, that's a design smell because it's like, it smells, it's bad, it's going to rot, it's going to, you know, hurt us down the line. So that's sometimes how we refer to bad design. If it contains elements that look like particular habits or patterns we're used to, where we're like, that's not very good. And we'll talk about an example of what some of those are. Why is well-designed software important? Well, at the start we said, you know, that it's about help, you know, makes your team's life easier and it makes your life easier as well. It's raining. As well as, what do we say? What was the starting point? Yeah, makes your code less likely to break. It's exactly what we just said. Cool. So some interesting stuff. If you like Google this and you read about it, you read about poorly designed software all the time, right? Poor software quality costs more than $500 billion per year worldwide. You could also call this lecture good software quality, right? Like writing good software, high quality software, all of these things, they're all just again about making code resistant to the tendency to break when it changes. People do studies on this stuff all the time and they look at, you know, what is the cost of actually having to like have poorly designed software? And you might be wondering, how does like poor software quality cost $500 billion per year worldwide? Now that's a crazy amount of money, right? I don't even think there's an Australian company worth that much money if you tried to sell it. So it's a massive sum of money. And a big part of that is because, you know, when you're a software developer, you go to do something, right? Like maybe you have to go and implement a feature or you have to go and build a system. But as part of that building the system, you're either working with code that is so poorly designed, i.e. it has such a high tendency to break, that you're constantly fixing it and working around it, or you're having to go into that poorly designed software with those design smells and fix it yourself. So now you're getting distracted. All of these things cost time costs money. Software design is therefore an interest for investment in a lot of people, for a lot of people. So where exactly is this design thing? Because I think one of my problems with the topics on design generally is that the word gets thrown around a lot. You know, it really does get thrown around a lot. Like, you know, and even you say to people like I've been part of the software engineering program design review, and you talk to people about this, and sometimes you say, oh, software design, and they think someone's sketching out some kind of front end or some kind of page. And it's like, oh, maybe. And then you think about other types of software design. And the other two I've got written down here, which are the other most common ones, are that it's the kind of software design that happens before you code. That's like the thoughtful planning. So like, you know, yesterday I was designing some software and I was designing it with a whole bunch of flowcharts and like sequence diagrams and documentation. I was basically writing software in Google Docs over 3 pages with like Miro diagrams. And it's like, that's software design when you say, let's think about this system at a high level before we write it, so we get it right, so we can think about the components here and we're not just bashing at it. And that's not always the right approach. Sometimes there are like better approaches. Sometimes it's good to just jump into it, but let's say for the sake of argument that it's good to think about it before you write code. But the other type of design you hear about, and I think it's important to contrast these two, is the design that happens during your time coding, which is about making your code itself more robust. Robust as in not brittle, right? If you think about like what's a robust thing, it's like this random Google water bottle that my friend gave me is robust. I could probably drop it and it will be fine. So robust means strong, resistant to breaking. Now, these two things are kind of interrelated, but also like when you talk about some examples of good design, it's very much before you code, and other ones are very much whilst you code, and there's a lot of gray area here. So I'm not trying to come in today being like, this is good design, this is not good design. It's a broad topic. And depending on what you're doing, you could argue that this stuff matters more. And for certain types of software you're writing, this stuff does matter more. If you can plan the system perfectly, then writing it's trivial, and it's very hard to write bad software. Like I've written software that 90% of the work is just deciding what you're going to code, and then the coding part's trivial. Examples like that tend to be things that are very mathematical or logical, because it's kind of like once you get your approach down, once you get your algorithm done, writing it's just a formality. And I know there's a handful of you here that are either doing 2521 or have done 2521, and it's like the exact same thing, right? It's like most of the time you can spend just thinking about how to solve this problem, but actually like converting pseudocode to code is like kind of trivial once you get used to it. Being water bottle, yeah. Okay, so that's where design falls in our spectrum. Now this is the last slide of Babel. Last couple of slides of Babel before we get into a lot of coding examples. So I've broken this up here into like the design, which is the thoughtful planning component, and the design, which is like the robust coding component. Now, in terms of this thoughtful planning stuff, we don't actually cover a lot of this today. So when we talk about this top one here, most of that we don't do in the course. There is some stuff we do later in the course, right? Though we do talk about some use case modeling, which is super useful. We do talk about some state diagrams and other kind of system analysis in like week 8 or something like that. But a lot of software design is just in planning, and there's no formal structure to it. We started to write some design docs yesterday for something, and it's just a Word doc. Sometimes it's a lot of text, sometimes it's diagrams, sometimes it might be pseudocode. It's all quite variable depending on what you're doing, but the point is you're probably not writing code that compiles. That's at the core of it. That's probably the only commonality I could describe to you. But so we could sit down here and we could be like, let's look at UML diagrams or state transition diagrams or sequence diagrams or use case diagrams or like, these are all just words that categorize diagrams of any sort. And you all know how to write diagrams. It's often a series of boxes connected by a series of lines in some way. So it's just some kind of documentation like that. The only one you've probably been exposed to, at least I'd hope, unless again, some of what they teach you in 1511 has changed, is writing pseudocode, right? Not in any excessive depth, but actually sitting down and going, all right, well, let's just write out what I'm trying to do at a high level. So, if you have, I got VLab open here. If we open up gedit, it's like, all right, well, I'm going to have a function called, register, and all that function is going to do is it's going to check if email is valid, check if password is valid, check if first name is valid, check if last name is valid, return 400. If not, you might be writing stuff out like this, right? So this is one of the main ways to kind of plan before you code. Add new user to data store, return new user's data ID, create new user ID. So, you have something like this, and it's like, all right, well, this is a form of design. This is a form of thoughtful planning. Again, we're not writing code, we're actually thinking about it. And the reason we like to do a lot of this planning stuff is a couple of reasons. One is, you can put this in a piece of documentation and other people can understand what you're doing later down the line without having to read your Python code. Because maybe someone doesn't understand Python. Maybe you've got a new developer who hasn't worked with Python before. Maybe your Python's really complex and that there are dozens of lines of code. So you want something really simple that just conveys the high level. That's the reason we might write something like this as pseudocode. And this is great practice. And I would recommend you do this as much as humanly possible. Like, you should definitely do it. You should definitely do it like before you write code most of the time until you're really comfortable with it. And I still do this. You know, if I'm writing a function that's going to be more than 20, 30 lines of code, I'll still write it down like this. And I'll leave it in a comment in the code because it just makes your life easier, basically, which is a good thing. So, yeah. That's thoughtful planning. We cover more of that later in the course. Most of what we're going to be talking about today, though, is kind of robust coding in the context of software design, right? Like, we want to write code that we think is resistant to the tendency to break as the code changes. It's quite a sentence, isn't it? You know, it resists the tendency for code to break as it grows or changes. Yeah, so just because you plan software well doesn't mean that when you go to write it, it's going to turn out well in its execution, right? You could have well-designed code that looks like crap. So a lot of today is really about the coding front. It's a very practical kind of talking about good software. So we're not talking about documentation. This is all from the moment you start coding to the moment you finish coding. You want to write stuff that is beautiful, just makes you proud. This is probably like a slide I can gloss over to, which is just like, why do we write bad code? So it's like, okay, you design some software, you plan it all out, and then you go to write the code and the code's terrible. Like, why do you do that? Or sometimes, why do you even skip the planning? And the short answer is, most of the time you're under pressure. Like, it's not complicated. You've got stuff to do. You've got a uni deadline. You've gotten given a work deadline. You only have so many hours in the week. You don't want to stay up overnight or on the weekend catching up on things. Or you say, oh, I want to design this well, and someone who's supervising you is like, no, I don't want you to. I need you to get this done in a week. And you're like, a week? This needs like 4 weeks to be thought out. And they're like, you know, get it done this week. We don't have another option. And you go, okay, and then you write some like bad software. And to an extent, like, this isn't a lecture on you need to always write well-designed software, because that's not going to be up to you a lot of the time. The point is that if you have the time and the space, here is the direction that you should go in to write better and better software, which we should all aspire to, and we should all get very excited about, right? So, yes. Now, anyway, onto some like software design practical elements. We're going to go through a series of these. We've got dry, we got KISS, we got minimal coupling, top-down thinking, refactoring, and then we're going to get into like the more clean coding part. D-Roy says, good code has inertia. An implementation at rest should stay at rest unless acted upon by net changes. Yes, good code has inertia. I've heard that somewhere. But that's a good point, you know. And, you know, it's like good code encourages good code as well. If you haven't heard this, it's like, have you all heard the whole, like, if you like clean your room because you'll keep clean rooms clean. Clean the kit, like, you keep clean things clean. You keep elegant things elegant. There's like a human tendency to try and maintain order in most things you do. You know, like that's kind of the whole make the bed thing. I don't make my bed. I haven't made my bed in years. But like, you know, you make your bed in the morning, and it's like you're setting a tone for, you know, the kind of day you want. You're establishing order in your day, and therefore you will continue to establish order in your day. All that kind of stuff. So let's get into the big conceptual things. Now, to contrast here, because just before I get into it, at the start of this lecture, I said that there's like a design element and a development element. Now, and then in design, we said there's a thinking element and a planning element and a coding element. So what this lecture is actually consisting of is we're basically saying, let's talk about some like designy codey stuff, and then let's talk about some development codey stuff. The difference between those two is when we tend to talk about software design in terms of the coding design, the simplest way to contrast that is often when we say that we are thinking about how our code is across an entire file or across an entire series of files, right? So it's thinking very big and broad with your software. Whereas when we talk about like clean and easy to work with software, we're going to be talking more about kind of like specific segments of code. Like you could add little snippets here and there in a vacuum, right? So that's the main difference. There's more stuff to talk about later, but design is looking at all your code or thinking about it all at once, right? You can't just say, oh, this 3 lines of code is well designed. It's like, I don't know how you could say that. So let's get back into it. Let's talk about some. Don't repeat yourself. Now, this is something you probably already know. I'm just slapping a name on it, or maybe you already know the name, or maybe it's a different name to what you're used to. But don't repeat yourself is simply reducing repetition in code. In 1511, they would often refer to this as removing magic numbers from your code, because that's kind of the easiest way that you can get first years to think about not repeating yourself in code. And that's kind of like one of the biggest philosophical ideas of being a good programmer, is that you should not, if possible, ever repeat yourself more than once. You know, if you have the same piece of code doing the same thing in 2 places, turn it into a function. If you have the same variables in different places, pull them out into some kind of, you know, global variable or configuration file or something like that. So don't repeat yourself is one of the easiest ones. Every piece of knowledge must have a single, unambiguous, authoritative representation within a system. Now, that's a very formal understanding of what this is, but it kind of makes sense, right? A knowledge is variables or functions, single, unambiguous, one place, authoritative, one place, representation within a system. Representation is a fancy way for just saying, you know, it exists somewhere. Why do we care? Well, like, why do we repeat ourselves less? And again, you probably know this from your own experience already, is that when you repeat yourself less in code, a change in one module is unlikely to break other systems. So if you have, you know, kind of constants or constants or magic numbers throughout your code, it means if you change one of those numbers, it's likely to cause an issue with the other numbers. Or if you need to change that number, you're going to have to change it in a whole bunch of places, which means you're changing lots of code, which means you might make a mistake, etc. So when you repeat yourself less, you have to change less. And the less you change, the less you have to change, the less likely it is for things to break. Because this is kind of a common theme with software, right? It's like poorly designed software breaks when you change it. And you also have to change it more often sometimes, because it's all kind of messy. So what's an example with dry? I've got this coding example here. We're gonna have a look at this. So we're gonna have a look at a whole bunch of coding examples together in VLab. So let me just pull VLab up in some more detail. Also, just while I pull this up, I hope everyone is settling into iteration 2 okay. I've noticed a lot of people are trying to get their head around the Flask stuff. It's certainly a little bit of a learning curve, you know, like it's not the easiest thing in the world. There's kind of a lot to take on, but you can pick up on it pretty quickly too, at least the basics. And I pinned a couple of posts on the forum about it, and it's going to be talked about in tomorrow's lecture. Because, you know, we've got Jake doing some of the auth stuff, which includes some Flask examples. I'm going to be doing some more Flask examples tomorrow too. So if you kind of have some thoughts and questions, there'll be space to talk about it. Don't you worry. Sorry, I don't know why I pulled the tutorials code. That's not what I meant to do. I meant to pull the lecture code. That's what happens when you're talking and you're distracted. Oh, that's not good. Sorry, give me a sec. Okay. I'm missing the code. It's sitting on my laptop. Give me 30 seconds just to grab it. Sorry. Oh, hey. This hasn't happened to me in a while. How many people have done that? How many people have written code on Git and then like forgotten to push it? I don't know if it happens to people who are like working alone or people who are you know, there it is. Here you go. Here's what happens with Git. We've got a terminal here, and it says my favorite thing in the world, which is your branch. Oops. Which says your branch is blah 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 ahead of master. So classic case of you commit code, but the push fails, right? Who does that? I do that. Sorry about this. It's a lot of code today, so I just want to get it pulled. So in terms of this dry example, what I want you to look at here is have a think about in what ways we could repeat ourselves less with this code. Because again, in C, or what you might be used to from 1511, you will just write code and then you'll pull out the magic numbers, right? That's kind of like one of the more basic things you do. But with what we're doing here, what we'd like to do is not just pull out the magic numbers, but really, really avoid repeating ourselves. So we want to go and simplify this entire piece of code here, right? That's what we're going to be doing. So let me just pull this and open it up. So think about it. I need your advice. You're going to guide me on this one. You're going to tell me what you want to see. You're going to tell me what you want to see in terms of making this code easier to understand. Oh, that's a different example. Oh, these are different examples. Oop, don't look at that. There's a bunch of different ways, but it's like, okay, let's first like have a look at what this piece of code does, right? What this piece of code does is that it imports sys, and then it uses sys to get the argv values because we want to read something in from command line. Okay, so we look at argc, which is defined as the length of sysargv because argv is a list. We check, is the length of sysargv not equal to 2? If it's not equal to 2, we sys.exit. If it is equal to 2, then we pull out the variable. Because remember, if argv is 2, it means we've gotten one argument, because the first argument of argv is always the file name itself. So we get that argument, the num. So we might invoke this this program like, I have to save this. Yeah, save this first. I might invoke this program like Python 3 dry, and then I give it a number like 6, like this. Okay, so we pull that number out, we convert it to an int because everything argv is going to be, it's going to be a string. And then if the num's 2, we loop between 10 and 19 inclusively. We set the result to be I squared, and then we print out the result. And we do the same thing for 3. So basically this one is like printing out the squares of all the numbers 10 to 19 inclusively. And this one is printing out all the cubes of numbers 10 to 19 inclusively if you enter 2 or 3. And if you don't enter 2 or 3, the program crashes as well. Okay, so we've got our first kind of hint from Daniel about what we want to do. Turn the for loop into a function and pass in the number. Hussein says use num instead of hard coding in 2 and 3 in your loop and printing. Okay, well, I mean, let me just start with that one. Well, let's start with Daniel's. Daniel says, turn the for loop into a function and pass in the num. Now, this is actually really interesting because, like, again, this is an example of why software design can be so topical. Like, you can talk to people about software design for hours because immediately Daniel and Hussein have both said kind of the right thing, but they'd start taking you in a different direction. Now, one thing I'm going to jump to, which I normally talk about at the end, but it's just occurred to me, this will make sense, is that we talk about all these different things in this lecture, but the last thing we talk about is this concept of refactoring, which I'll kind of come back to in a sec. And refactoring is the restructuring of existing code without changing its external behavior. So you might be used to hearing this word. Some of you would be very familiar with it. Some of you wouldn't be, but refactoring is a process where you kind of just look at code and you say, I want this to do the exact same thing, but I want the code to be better designed and implemented when I'm done with it. And that's kind of what we're doing here. I'll touch on that later, but this is an example of refactoring. We're not trying to change what this program does. We're just trying to make it better. We're trying to make it high quality software. So let's start. I'll start with Daniel, who says turn it into a function, because Daniel answered first. And yeah, let's call it like print powers or something. And it's going to take in what? It's going to take in the power. Is it the exponent? Is that what it's called? I forget. Is that what an exponent is? Or is it the base thing? The 8, 2, the 2 says... who cares? You'll tell me if I'm wrong. So we have like the exponent here. And it's like, well, what do we want to do? Well, we would like to go for I between 10 and 20, result equals I times by exponent. And then in the F string here, we just put exponent. And then it's like, okay, well, we just generalize that. So we're repeating ourselves less now. So if num equals 2, we can just say print powers 2, because we pulled that out. And if num equals 3, we can say print powers 3. Okay, so this code's getting there. Now, generally speaking, it's always good practice to put your functions above all of your running code. So like after your imports, before your running code. So that's kind of like a good pattern here. Because the thing is that like all of this stuff here is defining stuff your code can use when it runs, and everything here is kind of your code running, so it's a good reason to separate that out. Hussein says use num instead of hard coding 2 and 3 in your loop. So we can kind of generalize that, and Tawaka has answered that, which is kind of like here we could actually say, you know, if num equals 2 or num equals 3, then let's just print powers num, because that'll handle both of those cases here. And then we still have the else case like this. Okay, so the code's getting cleaner and cleaner now. Another thing you can do, I think, that works, and again, I don't code in Python every day, so apologies if I've gotten this wrong, but if you're ever saying like if x equals something or x equals something or x equals something, a really common, this is more to do with clean code here, but like a really common way to simplify this is just to do something like this. You know, if num's in this list, I can see that Hussein said if num's in a range, that's the same kind of thing. But this also works fine. It's basically saying like, you know, check if num is in this list. So if it's 2 or 3, this is often a lot cleaner if you kind of have more than 2 variables. I definitely say that doing a check like this is probably, I would say you should do it if you have more than 2 things you're checking. With 2, it's, you know, I don't think anyone's going to hang you up for it, because it's still pretty readable otherwise. So we're trying to repeat ourselves less, but let's not focus on other random details. Let's focus on repeating ourselves less. So what other parts of this code here are we repeating ourselves with? Can we do better? We're all thinking, I like to think. Thinking hard. What we should use a tuple here ideally, right? Oh yeah, I guess so. That's true. That one you wouldn't really be bothered about too much because you can't modify it, but that's probably clearer, yeah. Okay, so here's the question I want you to ask yourself. We're sys.exiting twice, right? Yep. Length of sysargv. Give me some pointers. Give me like what you would do. Like, do you think this code is don't repeat yourself enough? Do you think this code needs to be improved? That's kind of the question I guess I'm asking. Okay, Eric says, if lang sys equals 2, put everything in an if statement, else sys.exit. Yeah, I mean, so this is you know, let's look at this. Let's say, all right, well, if length of that is that, otherwise we put it in an else statement. The problem with this now is that you still do need to check if the numbers in 2 or 3, right? And you can't really like, yeah. And so Tawaka's kind of gone down a trap that like is really obvious here, which is you say, okay, well, if length of that is 2 and that is true, whoops, you know, and num is in 2, 3, then we want to print powers. But the problem here is you have to convert num from an int, from a string to an int. Now, obviously, you could do this. That's one way around it. Instead of converting it from a string to an int, you could just, you know, do that. That would work fine, though. Generally speaking, it's, well, sorry, no, it wouldn't. Still got to put sysargv here. Lord. Well, now the problem is you're just repeating yourself with sysargv, right? Like, there's a certain point with some of these things. Oh, now you got to convert it anyway, and then there's a chance it could fail as well. Well, no, there's not because it's an int. But like this code, you wouldn't call this code cleaner, right? Like, I mean, it's a different direction, but it's just got different problems now. Now you're repeating sysargv all over the place, and all you've done is save sys.exit. So there's some ways you could possibly get around this, but the point for this is more just to get you to think. It's not that it's fundamentally broken. You know, what we kind of had here isn't too bad. The one thing that sometimes students suggest, which none of you did, which is good, and we talk about this later, is they make a function like this called exit, and then they say sys.exit 1 or something like this. You know, and then they just put exit here and here. Now, I'm going to talk about this. I'm going to talk about this later in the slides, but this is what I would consider to be bad, and the reason I would consider this to be bad is because it's what I refer to as a benign abstraction, where benign means, where is it? Yeah, none of these are what I want. Maybe I'm a moron. Harmless, it's like it doesn't do anything. You know, it's like it's uninteresting, it's unprofound. It's you call it a useless abstraction is probably like a better way to a more clear way to describe it. But it's like you have abstracted away sys.exit, and for what reason? Because you wanted to have less characters in a line of code. Now, everyone does this. Literally everyone. I don't really see people not do this. And usually it's done under the proviso of like, what happens if I want to expand what this does? What happens if I want to add more to what exit means, you know? And that's true if you're kind of certain you're going to do that. But if you're not certain you're going to do that, here's what you've done. And here's why you have to be careful with this kind of stuff when you're trying to repeat yourself less. You still have 2 exit functions, right? Redundant abstraction, it's like, that's true, but it's not like, I don't want to call this a redundant abstraction. It's just like, it doesn't do anything. You know? It's just not doing anything for you. It's like just a layer. It has no it brings no value to the abstraction, right? So here, you're still repeating yourself anyway. Like, you're always going to repeat yourself in code somewhere because you're always going to be repeating function calls or something. The problem with this, though, is that you got to imagine, as a Python programmer, you know what sys.exit means, right? You all probably know that by now. Not all of you, but like many of you probably know that by now. So when you come in and you say, I'm going to now define a new function, someone reading this, while you think you're repeating yourself less, what ends up happening is that people know what this means, but they actually have to go and figure out what exit means. Like, they literally have to go and figure that out. They're like, what the hell does that mean? I have to go look up the function. So you're essentially adding layers to what they need to understand, because as a programmer, when it comes to not repeating yourself, don't be afraid to necessarily repeat things that everyone understands as well. Particularly if like all you're going to do is abstract it into a function. If this was more custom logic, it's probably okay. If you're doing something that no one already understands, it's probably okay. But all you've done here is add a layer of complexity here that someone needs to go and make sense of. So, you know, this is like fine as it is. This is an example. This lecture used to be swapped around, but because of this week we've changed things around. So we won't go through that example, but you'll kind of see that one tomorrow. But don't repeat yourself is a fairly straightforward concept. Jake says from sys import exit. Possibly. You see a lot of import sys, like with a lot of sys code, you see like import sys. You don't see a lot of from sys stuff. I don't really know why that is. My guess is because the sys library has so many like vague words in it, like exit, which could be misinterpreted potentially. Whereas like date time's not really misinterpreted. So you see a lot of import sys, but I don't think it matters so much. Hussein says, seems like a good example of Goodhart's law. When a measure becomes a target, it ceases to be a good measure. Oh, that's philosophical. I like that. So let's move on to keep it simple, stupid, right? Or like the KISS principles. So the KISS principles say that a system works best when things are kept simple, right? There's a general belief under a kind of KISS principle that complexity and errors are correlated. So your aim is to write the simplest, use the simplest tools and solve a problem in the simplest way. There should never be awards for doing things complexly, right? Like every time you produce a piece of code that isn't understandable or is super complex or super intricate, it's like a badge of shame in a way. Sometimes it's unavoidable. And when I say shame, I don't mean like, you should hate yourself or anything, but like you go into it and you're like, I don't like how this looks. It's like, a house of cards. Like if you can't see again how I've stacked up my, I don't have a mirror, but it's like I have this like stack of stuff holding this camera up, And it's like, yeah, it works. Well, look how elaborate it looks. But it's like, no, it's just going to fall over at some point. It's going to break my monitor at some point. So it's like, simple is good. There's a quote I love, which is that every line of code you don't write is bug-free. Because, it's kind of funny, right? We spend all this time thinking about, oh, how do we test our code and how do we verify that our code works and blah, 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 blah. But in reality, what's even easier than writing good tests for code? You know what's even easier than having coverage pick it up? Not having the line there at all, right? Like if you don't even write the line of code, because if you do something that you could do in 20 lines in 10 or 10 lines in 5, that's less that has to be tested. And if you don't write it, it can't break. It's bug free. So your aim in general should always be to write less code. And we care about that because, again, complicating things with boutique solutions means more code to maintain. The more code you have to maintain, the higher its tendency will be to break when there's changes to the code. And more code written means more code to test. The more code you have to test, the more likely there is to be errors in your tests as well. Okay, now, how do we keep it simple with code? Well, this kind of gets broken up into two categories, right? You have the whole, like, someone looks at your code and they say, you could do this a simpler way. And in some ways, that's kind of what the clean code stuff we're going to talk about at the end is. Though, we all kind of get that. We get that, like, you've written code before and then you've gone away and you've come back and you've written the same thing but with less lines of code. And in fact, we kind of did this as part of our dry example too, right? Like, less repetition is simpler code too. But the main thing I want to touch on is the use of, like, applying this philosophy when it comes to the use of libraries, right? Because as an example here, this KISS example, write a Python function to generate a random string with up to 50 characters, right? So it's like, if I have something like this, I want to write a function that generates a random string. And it's like, okay, I'm just going to get this back to where it started. Okay, so it's like, sweet. Right, well, let's, random string, and let's just call it here, random string 50 or something, or 40. Okay, how do we write this function? It needs to generate a random string with up to 50 characters that consist of lowercase and uppercase letters. Right, well, we could write this ourselves by saying, oh, I know in Python there's a random library. Cool, so I'm going to go look up, like, random number generator in Python, and it'll tell me to import randint from random, and it'll give me some example about, or maybe I'll just show you, import random, random.random. There's a randint function, here you go. Random.randint between 0 and 10. Oh, great. So Python's already got some stuff for me. So I don't want to write my own random number generator. I don't even know how to do that. But let's import it. So we're going to... Whoopsie. So we're going to say here, from random, import randint. Or you could import random and then just do random.randint. But regardless, let's print out a random number. Return randint 150. Okay, and we'll just print the result of randint 40. Oh wait, we don't need to pass in anything, sorry. Yeah, so it generates a random string with up to 50 characters. Great. See if this works. Okay, it prints this 9, it prints this whatever, Now, this is just to demonstrate that the random number thing works, right? But let's actually say, well, what do we actually want to print? Well, we want to print, it says lowercase and uppercase characters. Well, great. I mean, let's define them ourselves. Let's say that all of our chars is equal to, A, B, C, D, F, G, H, I, J. And then let's do the exact same thing uppercase. Right? Like, here's all our characters. You see? So we do all our characters like this, and then what we'll do is we know we need 50 things, so let's make a for loop for I in range between 0 and 50. Each time we do that, we're going to find a random int between, say, 0 and the length of chars, and that's going to give us a number, and we'll call that the index is equal to that, and then we'll get our char, which is going to be, just call it char, I don't like that, oh, okay. we get our char, which is going to be our char's index, and then we're going to append that to a string. So let's call this like, the return string is blank, and then each time we do that, we say return string plus equals char. And then at the end, we return string. So we just made this like random string generator. That was pretty easy. We didn't need much. I've got an error in my code. String is not callable. Oops, sorry. Oops, capital Z. Right? So you do this and you say local variable index, and you sit around with this for a while. I did that wrong. So I'm thinking about 4 different things. And then we get some random strings, and it's like, oh, isn't this cool? And it's like, you could argue that you kept this thing simple because you use the random library. And that's true. This code could be worse. But what you aren't doing here is you aren't leveraging even more libraries. So like a good question you can ask yourself, and the simplest question you can ask yourself when it comes to keeping code simple is, am I using libraries where appropriate? Because every time you use a library function, that's less code you have to write. And in this case, probably not, because, and we don't expect you to just know this off the top of your head, but in Python, if you look at like the string library, in Python, I mean, you don't even have to go very far. You can actually see this, like it's like right at the top of the screen, right? You can see that the string library actually has some what we call static fields for ASCII lowercase and ASCII uppercase and ASCII letters. And ASCII lowercase is just this. It's just a string of that. ASCII uppercase is a string of that. And ASCII letters is just a concatenation of those two strings. And it's like, someone's already done this for us. We don't need to write that. So I'm just going to go here and say, well, actually, let's just import string. And let's just print out what string.ascii characters are. I'm curious to see what this is. Oops. ASCII letters, sorry. Letters make sense because it's just the letters of the alphabet. There's all my letters. I didn't need to write that. So it's like, damn, Great. Well, that was easier. And I only use this once anyway. So like, I don't need, again, this is like pointless abstractions here. I don't need to pull that out. Oh, I do. Sorry, it's used twice. I missed that. Now I do. Now I should pull that out. That's better. Okay. So now I'm using that. That's even simpler. Can we simplify this even more? Well, it's like, all right, well, now you might do some Googling. Random string generator Python. Sometimes you're not going to figure things out just by looking at a library. Generate random strings in Python. You see some stuff here. They've got some for loops or whatever. We've got for loops too. And then you look at this and you're like, oh, wow. Oh, wow, look at this kind of thing. Look at this line of code here. So you think, oh, could we even keep this simpler? Could we use less of our stuff? Now, to be fair, what I will say is that, what we've done so far is the most important thing. Using libraries where appropriate is critical. This here just does improve it slightly, So what this kind of line of code here is actually concerned with is that you got to think about what, sorry, my VLab's being just a little bit slow, or the lecture is, or my internet's sending it to you. You look at something like this and you see this thing here called random, and you're like, all right, what is random? All right, well, let's print it out. Let's say this is actually producing a list, right? And we'll just print the list and take a look at it. Now, this is a funky way in Python of writing out a for loop. It's one of those things that once you get used to, it makes a lot more sense. But basically here, what this is saying is that for x in range from 0 to len chars, I want you to grab this list, which should just be chars, right? And randomly pick one. So random.choice is essentially a function that takes in a list and chooses something randomly, right? And in fact, we could actually clean up our own code to do this as well if we wanted to. Like inside this loop here, instead of doing all this random stuff, we could actually just say like, I know I started writing that out, but we could just refactor our own code to do this too by changing this randint and chars to just saying random.choice, because that just picks it for people. So great, let's actually print that out and see what random choice gives us. Oh no, does this need to be in... List comprehension's a weird topic. Oh, I don't need to import it too. Import random and import choice. Okay, so there's all our letters, right? And what it's done here is it's randomly picked those characters 50 times. Oops, sorry, this should be... Yeah, length... Oh, this should be 50. My bad. Because we want 50 characters. This is a bit random. What I've done here is I've mistaken this like length here for this 50, because this one should be 50. So it's like, you know, there's my 50 characters now. Right? Cool. Sorry, I got distracted. There's noises outside. Okay, so it's like, there's my 50 characters. Now all I have to do is join them together. How do you join them together? Well, you could go through a for loop and join them all, right? Like you could say, you know, for each thing we want to join it. Or you can use another method in the string library called join. Join. Surely that's somewhere else. String.join. Yeah, so what string.join does is string.join basically takes a string, then it does .join, and then it takes in a list. And what it does is it joins that list with that string in between everything. So what I could do here, for instance, is if I said, well, I'm going to get a comma here, and then I'm going to join my list with that comma. I think I wrote, yep. What this will do is this will take every item in the list and it will slap that string between every item. And then what we'll end up with, right, is this kind of like comma separated list. And I should just return that actually. Right? There's the list. But we don't want it to be comma separated. We just want it to be separated by nothing. So we do that. And it's like, bam, there you go. And then if you want to be real cowboy-like, then it's like, all right, well, I'll just put this with the brackets here, and then I'll just return that. And then suddenly you realize that you're actually only doing this once in your code. Maybe you're literally only doing it once. So then it's like, I don't even need that function now. I could just do that. Like if you're only using it once, you don't need to like layer all these things. Maybe you want to put this in a function. It's not a terrible idea, but you know, there's your code. Simple as anything. And you're only using chars once now. So it's like keeping code simple has this cascading effect. I think this line gets a little bit long, but you know, it has this kind of cascading effect where like suddenly you just have to write less code. And the less code you write, the less you have to worry about repeating yourself. The less likely there is you've had a fence post error. The less likely it is you're doing random correctly in all of this. Blake says, how come I can use the .join without importing a string? The .join is a function on a string object which Python will kind of quietly allow you to use without importing anything. That's why you can do things like, you know, some random string uppercase. String.ASCII letters is not tied to an object specifically. It has a lot to do with how objects work and how class fields versus object fields work. But the short answer is that this is like a typed variable. It's tied to the string type. It's not tied to a particular instance of a string. So to use that, we kind of need to import the string library. So there's a lot more to that though. Diorora says, do we have to reference quicker solutions we find online? Look, that's like, I get this question like weekly and I do it like all year. It's really hard. You have to ask yourself, is this proprietary is kind of the question you ask yourself, right? Like if you look at something and you realize that no one else on the internet's probably written this. This is probably like a super unique solution that was written by a person and then everyone else just kind of copied it. Then you probably should reference it. If you look at something like this, where, and again, you know, it's hard to know. You look at something like this, like I look at this and I'm like, this isn't complicated. This is just using a few library functions. If you gave me the random library and the string library and I understood list comprehension, I probably would have come to this eventually too. Maybe not this year, maybe next year, but like it's not like, you know, it's when I say proprietary, it's not like someone just like made it up, and if they didn't do it, no one else would find it. I think that's kind of the boundary here, because this is just using libraries intelligently. There's not a great deal of, you know, unique intellect being just demonstrated here. This is just someone who knows Python really well. So there's a very fine line, but that's kind of where the line is for me. But you can always just ask on the forum if you're not sure. Yeah, so there's our like keep it simple stuff. You know, and I won't go through this example because we're short on time and we can always loop back to it, which is like write a function that prints what day of the week it is today. You know, and again, this example is meant to demonstrate the use of libraries in the sense that here you could look up the date time library, because you've probably used this already too. It's like Python has a series of good date and time libraries where you can get the day of the week just by doing this, datetime.datetime.today.weekday. That gives you a number. You could then convert that to a string. It tells you right here. It's written in the documentation. Every time you come across these problems, this happens a lot with younger programmers, there's a tendency to be like, I'm going to go do something complicated, but it's like, don't. Because, you know, I don't know, I see this, like in the last 18 months, I hired a 32-year-old, a couple of 25-year-olds, a 24-year-old, and a 19-year-old to do work, right? And the 19-year-old was probably the most naturally gifted one there, but, you know, the code they wrote was often the most complex all the time. And I think it's a thing, like, I don't know, I haven't thought about it, but it's like, when you start programming, everything is really scary and hard. So you don't have a lot of confidence, right? And you kind of see this. What's that like what is it, like the false confidence valley or whatever? I can't remember. Does someone remember what this is called? I just thought about it. Confidence graph. Yeah, I think this is it. Yeah, it's like a thing like this where, you know, you come along and you start learning how to program, and some of you might have been like, you know, doing that just for a few months or like just this year. And because you get better at it, you're like, yeah, I'm better at it. And then eventually what starts to happen is, as you have to write like real code that starts failing pipelines and affecting group members, and you get an internship that breaks stuff, you start to kind of go, wow, actually, like, a lot of my stuff isn't that stable. And then you're like, damn, I can't write complex things. And you take a big step back and you're like, I need to keep things simple. And you kind of start moving through that curve again. So, I mean, that's a very broad generalization of this. But the point is, like, the reason we talk about a lot of this stuff is because some of you will demonstrate tendencies to make things really complicated, where you'll see something like this and you start being like, you know, yeah, okay, I know how to code now, great, let's start planning or like what I'm going to do. And it's like, no, you can just use libraries, you know. And I'm not attacking anyone here either, because it's just like, it's a thing that you see handfuls of people go through, which is pretty normal in your programming journey, in your kind of software design journey. And the most amazing thing about when you work with senior engineers, and I mean people more senior than me, their ability to just be so unremarkable is just so comforting. Like, you'll see them solve these problems and you'll look at and you'll be like, oh, that wasn't very like innovative. And it's like, thank God. That means their code's probably going to work. So yeah, anyway, that's kind of it on KISS. We're going to talk about a few other things before jumping on to cleaner software. Let's take a 5-minute break and start again at 11:15. And yeah, then we'll keep going. So let's take a 5-minute break. Hi. Yeah, welcome back. Is my camera in focus? Can't really tell. Yeah, that'll do. Hi, we're going to keep going on with this. I hope you're all... This is one of the longest lectures in the course, so bear with me. When we talk about software design, the next kind of thing that comes up is this idea of like there's be a bunch of different names for this, but like an idea of minimal coupling, right? What the hell is coupling? What the hell is minimal coupling? Well, coupling is the degree of interdependence between software components. And this actually makes a lot of sense, right? Like if you think about your project, which is probably the best place for you all to start visualizing this, is like in your project, you have an auth file probably, and a channel file, and a data store file, and a this file. And some of them are probably using each other, or even your tests are as well, right? Like your tests might be calling each other. Coupling is the degree to which these things are interconnected. So like you could get your software, you could sit down and say, well, okay, here's a Python module, here's a Python module here. You know, I'll draw them all out. And then you connect them all in terms of who uses each other, who imports each other. You know what it might look like this. This could be what it looks like. And coupling is the degree to which there are lines connecting these things. So a good design approach is to generally minimize that, right? Like coupling is bad. That's why we call it minimal coupling. Well, unnecessary coupling is bad. So when it comes to software, you want to, you want to provide some kind of, how would you put it? Like minimization of how things are connected, because the more things are connected, the more of what you'll find is that software tends to break when someone changes something, right? Like think about your data store. If you change your data store, you change the name of it, you change the behavior of it, the more people using it, the more likely things are to break, right? So therefore, we want to try and reduce that. Now, I haven't got any examples here because the examples would get very complex. Like we'd love to start with someone's software project, but that, that's kind of problematic. So graphs, yeah, you think about it like graphs. When we have a lot of code that's connected like that, we sometimes refer to it as spaghetti code. We call it spaghetti code because it's like a plate of spaghetti where everything's kind of like interconnected and all this kind of stuff. So you want to try and avoid spaghetti code. You want to try and avoid highly coupled code and have things nice and independent. Now, can you totally avoid that? Can you absolutely avoid code that is connected? It's like, no, there's always going to be code that has interdependence. And some of your code, like your data store, is just going to be interdependent by its very nature. It's going to have a lot of connections to it because everyone's using it. You can't avoid it. It's an important question of like, can I reduce this further? And one of the most common signs of this is when you have file A importing file B and file B importing file A, right? That sometimes happens and you should keep an eye on that with your own code. But then also just ask yourself, like, do I need to import this? Can I abstract it out? Is there other ways to do it? Again, I designed this not to have specific examples, but that's something to keep in your mind. There's more about this in other courses, but it's very relevant for your project because it's pretty much the first big software project you've written. Yeah, Blake says if your program has no coupling, then it's a bunch of separate programs. Exactly. There's going to be some degree of coupling. You just need to ask yourself, like every time you see software using another part of it, you ask yourself, can I avoid this? If the answer is no every time, then great, you've done your job. It doesn't matter what a web of code looks like. All that matters is that there's nothing unnecessary there or nothing preventable. Now, another really important thing about thinking about software systems broadly is what I refer to as top-down thinking, which is a similar principle to what you might read about online, which is you aren't going to need it, or like the Yagni principle, which says that programmers should not add functionality until it's needed. Okay, that's the principle here. So top-down thinking says that when you're building capabilities like a system, you start from the highest levels of abstraction, you work down through them. Now, a bunch of you would do this most of the time without realizing it. In a lot of ways, I'm just trying to formalize it. But what we mean here is that if you have, say, a system to build, like, your project, it's very easy to start going, oh, I know, let's build out a whole data store, and then we'll build out a whole series of helper functions, and then we'll go and write the interfaces and then go write the HTTP. That's what we call bottom-up design or bottom-up programming or some other thing like this. In general, we always want to try and do it the other way around. We always want to try and start at the interfaces and work our way down when we're actually developing it. So you've written your tests, you go to implement your routes now. You already have written some for iteration 1, but you got to write the new ones and actually work your way down. Now, there's a question here that I'm going to quickly chat to. We don't need to go into excessive depth with it because, we don't want to spend all time on it. But if we have this question here, which is, given two latitude longitudes, sorry, I just jumped ahead. Which is given two latitudes and longitudes. This is the finished one? Yeah. Like this. Yeah, that's it. That's it, Blake. I mean, I feel like for anyone who put up with me in 2521, I would have said a similar thing. But it's like here, given two latitudes and longitudes coordinates, find out what time I would arrive at my destination if I left now. Assume I travel at the local country's highway speed. Now, I like this question because it really demonstrates it very quickly. But let's say I have a function here called given two latitude longitudes. And what am I trying to find? the time I would arrive. So arrival time, something, lat long. What am I going to do? I'm going to return 1 to start. And then I'm just going to call it arrival time, and let's, if I left now, 2 latitudes, longitudes. Sorry. Well, let's pass this in as like two tuples or something. Arrival time. Well, we should be able to figure this out. Let's find like the lat long of Sydney. This assumes that you're traveling in a straight line, of course. The lat long of Sydney's, this stuff. So negative whatever, that we can make it 2 tuples, and then let's pick another one. Let's just do Brisbane. Okay, there you go. So it's like, this is you writing code here, and this is how you can start writing code. Yeah. Now, again, there's obviously going to be some library things here, but the broad point is that, okay, you have a function. Before you even worry about it, you just start writing it out. Yagni like this. Now, I forgot to print this. Whoopsie. Print arrival time. And again, how do you break this program up? Well, you say, all right, given 2 latitudes and longitude coordinates, find out what time I would arrive. So I need to find out the time. Assume I travel at the local country's highway speed. Well, what do you know about time? Well, you know that speed equals distance over time, right? So blah, blah, blah. Time is equal to distance over speed. So maybe you can write that. You say like time equals distance over speed. I know that speed is equal to 100, and I know the distance is equal to, distance between lat longs. And I can just pass those in. Now, once you do that, you can just return time. And then I'll go and stub this like distance between lat longs function here, which will take in the same kind of arguments. And let's just say it returns 100 kilometers. So this should say that it takes, an hour, 1 hour, right? Yeah, 1.0 hours. Now, the point of like writing software like this, and the point of, I refer to this as often, we've finished it, it's just not implemented, where we've actually written the function and we know what it does. The benefit of this is that it helps you think about the behavior of functions without getting too caught up in like the details of it. And we can say we'll delegate that later, and then you can keep delegating this kind of stuff further and further down until you're done. And if you think about this, it's kind of like, well, all right, you have this, you want to implement a function up here, so you implement all of it, and then there's a part missing. So, you just delegate that down here, and then for this part, you go and implement that, and then there might be another part missing, so you go and implement that. And it helps you just kind of narrow down on the problem you're trying to solve. And it's often consists of a lot of stubbing and whatnot. I would strongly recommend people try and approach it this way. Now, this might just be a more pleasant way to program generally, but the point of this lecture is kind of like well-designed software. So it's like, what is the benefit in terms of software design? Forget how you feel of this. And the short answer is that it often makes you avoid writing unnecessary code. Because you're starting from the top down, you literally only write what you need. Because if you start from the bottom and you start saying, I'm going to calculate this and I'm going to calculate that, and then I'll tie it all together, you often will write code that you don't need, or it's more sprawled or more complex than you need it to be. So it's not something you have to do all the time, and it's definitely not something that is always the right approach by any stretch, but it's a good general philosophy to follow, because it helps you make sure that what you write is what you need, right? And then refactoring, we talked about this at the start. We did this with the dry example where we, we repeated ourselves less, we refactored the code. You could argue we did this with the KISS stuff as well. Again, it's existing code without changing behavior. The hard question though is like, when do you refactor? Because refactoring is this very broad concept. When people refactor? Well, sometimes you write code and then you refactor it 5 minutes later. We kind of did that with the KISS example, right? We got it working and then we said, are there ways to clean this up? That's totally normal. You don't have to come into code and write it perfectly the first time and use libraries perfectly the first time. You can, that'd be great, but it's like, you can actually bash a little stuff out and then go and fix it up, So there's kind of refactoring in a few different ways. You can refactor it right then when you're writing it. You can refactor it just before you put in a merge request. You can refactor it as part of a broader project in week 5 over Flex Week, or at the end of the term, or at the end of the year. There's tons and tons of stuff you could do here. The one thing you need to be careful of is essentially trying to figure out what's like an appropriate amount of refactoring, because every time you refactor code, you're also going to break stuff. And this is kind of the conundrum of refactoring broadly, is that most of the time that people refactor code, it's to improve readability or to improve the robustness. So you're trying to actually refactor code to make the code better designed. However, why do we want well-designed code? It's to prevent its tendency to break when we change it. But when you refactor it, there's a high chance you're going to break it by changing it. And this is a really hard balance to get right, because the more you touch things, the more likely they are to break. Though the less you touch things, potentially the more likely they are to break as well. There's no short answers here, but that's the kind of conundrum you're dealing with. Now, in terms of, yeah, that was kind of it actually. It's just trying to figure out where that balance is, and it's a hard balance to strike. And Matthew, yeah, you got the top-down thinking problem right as well. Refactoring. It's a hard thing to do. I've worked with people that try and refactor too much. I've worked with people that try and refactor too little. Who knows? Maybe I'm wrong. Maybe they're wrong. It's a hard thing. No one will ever get it right. Okay, so that was all software design, right? So we said at the start that software design is about code that's resistant to breaking when you change it. We said there's planning elements, which we're going to gloss over, and then there's the coding elements, which we just spent the time on the last hour. The last part here is this development side. This is the stuff where I said you can write good code, good software in a vacuum. So you can actually write software that is correct because it's tested. It's well designed because, you've thought about how to reduce coupling, and you've gone and, made it structured well, and you've avoided repeating yourself. But it could still be written like garbage. It could still be absolutely terrible. Like, people could look at it and be like, oh, this is so hard to understand. And the reason we want to write nicer code, even if you get the testing and design right, we still want to write nice code, is because it's easy for you to understand, it's easy for others, and it's easier to spot errors in the future. Writing nice code tends to not really fix errors that much. Like, writing clean code tends to not make it as robust as having well-designed code, but it does actually make it easier to spot errors and stuff, because if you use, very universal approaches, very accepted standards, it's easy for other people to look at it. So what is clean code? Well, clean code's really hard because all the stuff we talked about with design, you could apply to most programming languages, right? You could apply it to Java and C and whatnot, whereas a lot of clean code is often very language specific. So some things we talk about here are you could apply to every language, like commenting. Other things you could apply to only a handful of languages, because not all languages have this particular feature. And then other things we can only apply to Python specifically, because it's a very Python specific thing. Now, there's a second slide here. In terms of what clean code is, generally speaking, it's code that's simple, understood, and following good conventions, right? We've kind of seen this already with Python. It's like, what's a good Python convention? Does anyone have any ideas? Like, what's something that's just like a standard way to do something in Python? Docstrings, we've talked about a little bit, but we'll go through some examples. Before we get into that, when we talk about following conventions, when it comes to Python, and we're talking about how do we write consistent Python code that everyone in the broader community understands, this is a topic which we refer to as writing Pythonic code. And what in the world is Pythonic code? So, it's written here, when someone who is a really senior, experienced Python developer says that this code is not Pythonic, they usually mean that this little bit of code in a vacuum does not follow the common guidelines that's kind of set out by the broader Python community, right? And what that means is that in the Python world, as part of kind of one of its language tenets, there's a kind of understanding that most problems have a general best solution. A general best approach you can do here that, people are like, yep, this is great, this is good convention. Now, this is Python specific. Python, more than any other language, probably has more of this in it, like more opinionated examples of what to do, though it's definitely true in other languages as well. But some of what we talk about today just falls into that being Pythonic category. But you don't have to think about that too heavily either, because other languages, while they won't call it Pythonic, they'll have their own accepted approaches, right? Like the C++ community has a set of accepted approaches as well. So, yeah. Okay, so one of the first things is docstrings. Now, we've kind of talked about docstrings with the PyLint stuff, and it's come up a little bit in terms of like the forum and people asking about it. Docstrings, the broad topic here of writing clean code is commenting your code, right? You comment your code, it's easy to understand. Some people could argue that's design stuff as well. It's all a big blur, but commented code is easy to understand. I always get the same questions too. How much do I need to comment my code? The answer will continue to be, as it always is, the amount you need to comment your code depends on how understandable it is. Most code needs commenting. How much of it needs commenting depends on how easy it is to understand. If you write well-designed, clean code, you don't often need to do as much in the way of actually interacting with like big blocks of comments. Now, in Python specifically, we have a certain convention of writing comments, which is what we call docstring formatting. You'll find things like this that are similar but slightly different in all languages. This one in particular with Python is pretty much you have a description, right? Up the top, which just says what the function does. You have a list of parameters, which tells you what each of the things passed in is. It's often a good idea to include their types there as well. And then you say what it returns, both in terms of the type and in terms of what it's actually returning. Now, in reality, these types are made up. That this doesn't mean anything. This has no impact on how your code runs. It's just documentation. But this is how you would write clean code in Python, because if you follow these conventions here, which is a big part of clean code, then other people are going to be able to pick up your code and follow that structure and be like, oh yes, I get how this works. Description, parameters, return statements, done, easy, done. There's not much to say on that, so I was just going through that fairly quickly. Comment your code. This is how you comment it in Python. Another kind of common way to write clean code is the use of our map, reduce, and filter functions. What kind of started to happen was that people writing some of these scripting languages like Python and whatnot noticed that a lot of the time people were using iteration, as in looping, for pretty much like the same things a lot of the time. And they kind of reduced it down to, it's funny, they kind of reduced it down to like 3 big areas, which was like mapping, filtering, and reducing. Reducing is a little bit different, but like we're going to start with mapping and filtering because that's a little bit more straightforward. Mapping is the process where you start with a list, and that list might have, say, 5 or 6 items in it. And what you want to do is for each item, you want to go and modify it in some way and produce a new list with those same number of items. So mapping focuses on constructing a similarly sized list, the same size list in fact, except there's been some kind of modification to each element potentially. And that's why we call it a mapping as well, because the reason it's a mapping, oops, where's my cursor? Yeah, the reason it's a mapping is because we're saying take this one and turn it into something else. We're mapping all of these ABCs to like DEFs like this. On the flip side, something like a filtering is kind of different. With a filter, we don't actually modify anything. So if I do a filter down here, we don't actually modify anything, but what we do is we decide which of these unchanged elements will appear in our next list. So if I take a list like this with 5 elements and I filter it, these aren't going to change, so I'll make them the same color, but what we'll end up with is a list with 0 to 5 elements in it, maybe 2. So a good example of filtering is looking through student grades and pulling out all the ones that are HDs. Or a good example of mapping is looking through all the student grades, or looking through a list of date of births and turning each date of birth string into a dictionary, which consists of both the date of the birth and the age as of right now. So we'll look at a couple of examples of these. And it's like, why do these exist? Well, the main reason these exist is because if I had a piece of code like this where I wanted to go through every tutor and I wanted to make them uppercase and put the exclamation marks at the end of them, what I would have to do to make that happen, if I open this example here, and let's forget this map for a second, is I would have to get each tutor. I would say that like my new tutors would be a new list, and then I would say for tutor in tutors, and I'd say new tutors dot append maybe an F string that has like tutor dot upper exclamation mark like that, right? And then I might print new tutors. Now this is like how you would solve the problem with the knowledge that we've taught you to date, right? you get like that. The thing is, this whole map reduce filter stuff, it really came out of the fact that so many people were actually just doing this kind of loop where they were just taking a list, looping over it, modifying it into a new list, and then printing that new list out. So someone was like, hey, let's not even worry about that. Let's just find a syntax for it generally. So what we can do instead is that we can say, I'll use the language here, is we can say that if we look at new tutors, we can say we've got our tutors list that has 4 elements. So we're going to create a new list with 4 elements with a modified set of values. So they've all been mapped to something else based on the same rule. So what we do is, and maybe I'll just break this up again on a few different lines, is we say new tutors equals map, where we give it a function and we give it the list. Where fn is like a function here that's applied to each element in the list. Right? So map says, take this list, go through it, one element at a time, and each element, it applies that function and it returns the value of that into a new list. Now what is this function? Well, this function could be anything. I could put something up here like shout, like this. I can just pass in a function as if it's like, a pointer to a function or something like that. So let's try something like this. Let's try this code. We got our tutors, we map it. Let's see what happens. I go and run that. We get this random map object. So the way map works in Python is that a map itself doesn't actually return you a list. It returns a map object, but thankfully you can easily convert that to a list by wrapping it in a list. And this will actually spit out the new list. Now this is super cool because, we've effectively mapped it now. We've taken a list, we've applied a function to every element. Super clean code, right? This is what I mean. I wouldn't call this like design as much because it's hard for me to think of design if it's just a few lines of code you could improve on. This is just writing clean code. Alternatively here we could use a lambda, which are a little bit confusing, where instead of defining a function like this, if you have a function that takes in one argument and returns something that's been modified, you could easily, instead of saying shout here, you could say lambda string. So this is now a function that takes in a string, and what I want it to do is to return me string.upper plus the exclamation marks. And this is the exact kind of same thing we did before. It's just, slightly different. Slightly different things, right? It's just the same. It's actually quite literally a function. Just doesn't have a name. So it's like, great. S here, return s.upper. Yeah, so Blake said, why would you want a map object? I think this will come up in week 10 more when we talk about iterables and other things. But essentially, when you have a map object here, when you do this, the mapping hasn't actually happened yet, because a lot of things in Python are designed to be much more intelligent. Because if you're mapping a billion items, you don't want it to kind of map all those billion items at once and like store a whole chunk of thing in memory, which is certainly going to be slow. So this kind of map object is like, it's like a map ready to go. And the actual converting of it to a list actually forces it all to be evaluated at the same time. You might be asking, well, what else would I do besides convert it to a list? You could actually iterate over the map, which means that it's actually kind of generating these things on the fly. It's like a memory saving thing, but again, this will make more sense when we talk about the iterable stuff later on in the course. And that iterable stuff later on in the course, isn't critical to you understanding things throughout the course, so you don't need to worry too much. So that's our mapping. But let's have a look at filtering, which is kind of similar but opposite. I've got the example here about student grades. Now, I'm not going to try and take you through this with first principles because it's kind of the same thing. What we do is if we have a list of marks here and we want to pull out all the passing marks, we can actually, similarly, say filter instead of map, and we give it a function which will go across the entire marks list, and it'll apply a function to it. And let's just write this function out here too. I'll call it def function, which will take in a mark. And all it's going to do is simply return if m is greater or equal to 50. And then we convert that filter to a list. And then that gives us our passing marks. Now this example is a little bit more thorough, right? So let me just put passing marks here. And if we run this code here now, Python 3 filter, let me just fix this up, sorry. Python 3 filter, we get 65, 72, 81, 56. So these are all the ones that are greater than 50. So a similar kind of thing. We take marks, we filter it, and again, remember the thing about a filter, it doesn't change the values. A map changes the values into a list of the same size. A filter does not modify the values into a list of a different, potentially different size. So quite often filtering is about just stripping things down and getting only some basics. Now, as part of this example, I also have a reduce function here, which I combine these two into the same example. But reduce is a little bit more complicated in terms of it doesn't behave like map and filter, because you need a starting value. It's very, very similar, though, a lot of the time. Well, it's very similar. It's just like the other two things are producing a list. But what a reduction does, what a reduce function does, is it takes a list and it turns it into a single value typically. And that's why we call it a reduce function, because you're taking this big thing and you're trying to reduce many elements down to a single value. Now, you often won't write reduces. That's probably like one broad advice I'd have. Doing maps and filters are kind of like the bread and butter of most things you'll do all the time. But most kind of common reductions are already written for you. So just as an example, let's say for a second that in this example, I want to get all the passing marks in the course. Okay, so I go and grab that filter here. I filter it down and I get those 4 marks. Now what happens if I want to add them together? Well, I could add them together by doing a reduction, and I'll actually just pass in another function here, because I think lambdas are okay, but I don't want to like get them mixed up with this concept. I'll create another function here called function2. Sorry, VLab's just a little bit slow. And what function2 is going to do, and this is kind of where the reduce differs, is it's going to take in 2 arguments, which are a and b. And then all I'm going to return here is a plus b. Now that might seem like a pretty strange function to write, naturally. But what it's going to do is this is going to magically try and reduce my things to 0. Now, have we got this right? Sorry, reduce it to the total. It's trying to sum them all up together. Okay, so reductions tend to want to sum things up or multiply things together. Sorry, I have to print it out. So what are we going to get? We should get a number that's like, 137, 81, 200 and something, 270-ish. Yeah, 274. So the reason this works is because what a reduce does, which is a little bit more complicated, is that a reduce will take something like your elements, like all your boxes here, like this. And then what it's going to do is it's going to kind of like take these two down, your A and your B. It's going to reduce them somehow, which in this case is adding them together into a new value. And then it's going to replace all of this with a new value. And then what it does is it gets that value and it grabs the next one and it adds those together into a new value. Right? It's just iterative summing. It's just going along on like a running total. We're all kind of used to this. You take a list and you keep a running total and you keep combining it together. Hussein says, is it basically a recursive function call? I don't want to give an assertive answer on that, but I think you can conceptualize it like that for sure. Whether it's recursive or iterative, it doesn't really matter. You can kind of think about it like recursively. It just recursively sums things up and like builds it out. Now you could do this for multiplication too. Reduction doesn't mean summing, it could mean multiplication. The reason the word reduce is important here is because you're reducing a list typically to a value, So it's that reduction from list to value. Now, again, how this function actually works here is that it doesn't actually take like 2 values, a plus b. What it's actually doing, and I can't get the order right here, but it's doing something close to like sum and value, where what this function actually takes in is it takes in the running total, which I might even call it that, running total plus value. Running total like this. And you know what we'll do? Let's actually print this out. I might have these the wrong way around. Someone will tell me if I do. Print running total and value. So let's print these out. And you'll actually see this function being called all the time. I'm pretty sure it's iterative, but I run it. And then you can actually see here 6572. So the first time we run it, the running total is just the first element. And it's trying to add the second element to it. And once it adds that together, we get 137. And then the next time we call it, it tries to actually add that one together as well, right? And then it adds the next one. So we're actually adding 65 to 72 to 81 to 56, and that's the number we end up with. So in this case, the reduction was called 3 times because there were 4 values in the list. Yeah, and we don't, yeah, that's it. So we don't actually need the list thing here because it's all kind of happening behind the scenes and we're not needing to, we end up with a value, not a list. So map, reduce, and filter, super useful. Again, you're probably not going to use reduce much in the scope of the work you're doing because there's actually reductions built into Python as well. For instance, we have a function already in Python called sum, which is essentially a reduction function where you could give it passing marks and it will actually iterate through it and sum it all together and turn it into a value for you. Like, you don't need to use the reduce here. The filter and the mapping are probably useful, but the sum is already built into Python. Liang says, can you pass in more than 2 parameters? No. So maps and filters take in 1 parameter, or maybe. Different languages might do something differently, but generally speaking as well, I'll just speak generally because I don't want to get too caught up in things, because you can go read the docs, right? Generally speaking, maps and filters take in 1 value, which is the value of the actual element that you're mapping or filtering. Reductions take in 2 values, which are the running total, which applies for sum, but it's essentially the accumulation so far and the value that you're trying to add to the accumulation. Matthew points out a good point as well about back on the docstring stuff, where like the other benefit of docstrings is that you essentially, like, if you have a standardized format, and this is true for other languages like Java and whatnot, it will allow you to it will allow things like editors and document generators to actually pull things out. So there's actually more value in the standard nature of how we define comments because it allows other people to parse it and read it. And if you do want to learn more about map, reduce, and filter and the specifics around, you know, how to use it, some more examples, parameters, return types, lambdas, like all of this stuff, you can go look it up online. There's a whole bunch of examples from, you know, W3 schools to random things as well. It's a principle you should apply because I'd say there's a programming philosophy that says that you know, cleaner code has less explicit iterations in it, less explicit loops in the code. So what you notice about the code here is while the code we have here is essentially doing looping, we aren't looping in our code. Because like looping is a common source of error. It's just an absolute common source of error. So these kinds of one-line generic iterative approaches are great. They make your code a lot better and cleaner and less likely to break as well. So we have just a few other things. Why is that blank? Oh, that's not good. I'll have to pull up another one. Just a few other things. We'll kind of bash through this relatively quickly. One thing, we've already talked about exceptions in this course because we had to run through it as part of your project, but one thing to point out is that generally speaking, you would consider that exceptions make your code cleaner. Now there's a big kind of topic, and I guess to an extent, like, I wouldn't call it a debate, but there's certainly a conversation to be had about this where with like a C style of programming, when you want to denote that something went wrong, when you want to say there was an error, you tend to return a value that denotes that error. You tend to return -1, you tend to return none or some kind of null here, like in early.py. The main benefit this brings is it makes code easier to be reasoned with. The reason I say that is because with exceptions, the one thing exceptions do that none of the rest of the code you write does is exceptions break the normal order of programming. So when you're writing code, you can typically put a pen on that paper and follow it in a very structured way. Here we go down, if this, else that, go through a loopy loop, jump into a function, return back out. However, exceptions can make you jump from one piece of code to a totally unrelated piece of code, depending on what's caught. That makes it very hard to reason and model with your code. That's why things like the formal methods and stuff, from my understanding, are easier to do on code that doesn't have things like exceptions in it, and go-tos are the same thing, because it's just like easier to follow the flow of it. However, most of us aren't trying to write, you know, formally verified code, or we don't spend that much time reasoning with code either. We want to spend a reasonable amount of time just having clean and clear code. Exceptions are useful because they just make your code easier to understand, because you're just like, here's the problem, there's some text associated with it, I'm not worrying about return types, because if this exception is raised, I'm like going down the error avenue. I'm not dealing with what's returned. I'm dealing with try and accept, sorry. And, you know, they're all separated like that. So generally speaking, exceptions fall into the clean code category. So if you're returning things like, you know, -1 to say that there was an error, it's like try and use some exceptions more. Thankfully, Python has a bunch of built-in exceptions again. You don't even need to import these. So, you know, you look at all the built-in exceptions. Built-in means you don't need to import anything. And again, there's tons of stuff. And if you're not sure what to use, one of the most common ones that you're probably going to use is value error. Because value error just says that, you know, there was a value given that was wrong. That's a really common one. I'm just pointing out that exceptions aren't universally better. There are times when you actually want to avoid exceptions because they can make code harder to follow the flow of. But generally speaking, you would consider them good. And then the last one, this one is very Python specific. This one is just multi-line strings. So it's like sometimes you need to have strings appear over multiple lines. You can concatenate those on multiple lines, but in Python, you know, some of you would have discovered this already. Rather than do something like this, you can actually, well, you can either do something like this with the comments. So you can use the big block comments with the 3 double apostrophes, which don't care about new lines. They kind of ignore new lines. They treat it as part of the string until you've ended that new string. Or if you want to break things across multiple lines, you could just do something like this as well. Because this is not something you'll come across a ton in your project, though you might come across this in your tests, potentially, depending on what you're trying to test. But yeah, that's really it. The last slide here was just on the abstraction stuff I mentioned earlier, which we kind of already went through, which was the stuff on the dry example where it was like, you know, you don't always want to abstract out the sys.argv1 into exit, because you're just creating an abstraction that adds confusion. And I mean, I guess to summarize that particular point, remember that every time you add an abstraction, you are asking someone to learn something else, right? You're asking them to make sense of something else. And you need to make sure that you asking them to make sense of this is a less effort than the kind of complexity or the confusion or the repetition associated with not abstracting it. That's the kind of the simplest thing. And that's why abstractions are often the easiest things to do, because 99% of the time abstractions are always less hassle than they save, you know. But there are a few times where that's not the case. So you just need to kind of be cognizant of that and keep an eye on that. Because, you know, that's important. Now, that pretty much brings us to the end. Do you have any, we got a few minutes, so do you have any kind of last questions before we start to wrap up here? Any last questions in the last few minutes? So just while we wrap up, it would be great if people could just fill in the survey as always, whether you're live or watching the recording. It's always super useful. Yeah, sorry that the internet seems to like it's starting to die. Sorry, there might be some congestion. So please leave some feedback in our last few minutes. Osama says, just to be clear, you need to be very familiar with the programming language to achieve a high level of efficiency, right? I'm going to interpret your use of the word efficiency here like clean code. Generally, understanding the nuance of a language better does help you write cleaner code, but that kind of comes naturally with time. There are certainly lots of things that you can translate between languages too, right? Like you learn Python docstrings and like, sure, that's Python specific, but when you go to like another language like Java, which has like the Java doc, it's all the same thing. It's just that, you know, the syntax is slightly different, but you already get what it's about and all of that. So that's pretty easy. Alex says, when will you explain the token in the assignment? So I've asked Jake to do that tomorrow morning. So token stuff's tomorrow morning and persistent stuff is tomorrow morning after Jake as well. The point of week 5 is learn a little bit about how to write better code. So try and if you aren't already, go about doing some of these things in your project for iteration 2. And tomorrow's about, let's learn more about auth and tokens. And let's learn about persistence. So that's what we're doing tomorrow. So you'll have Jake for the first hour and me for the second hour tomorrow. Anyway, 11:57. Please leave some feedback. We'll wrap it up there. If you have any other questions, just post on the forum. Otherwise, keep at it with iteration 2. Looks like people are making some good progress and people are starting early, which is going to be really helpful. If you need anything, please always feel free to reach out to your tutors. They're paid to look after you. And if you need anything else, you can always reach out to any other teaching staff member as well. But anyway, have a good day. And, you know, look after yourselves. Try and get outside when it's not raining. And again, to anyone who's in Melbourne or similar lockdown, I hope you're doing well. All of that. See you later.